Hello everybody, and I hope you can hear me well. I'm going to talk to you today about plastics and the circular economy. So I want to take, following on from Kara's really beautiful talk, to talk a little bit about solutions. What solutions do we take to plastic, and how do we stop it reaching the ocean in the first place? And I want to be able to talk about some of the funded research projects that we've got running in this area at the moment. Okay. So I want to start off. I work in the Global Systems Institute at the University of Exeter, and it's full of multidisciplinary scientists, including climate change scientists. And we have this discussion quite often. Why bother with plastics when we've got climate change to deal with? I mean, we've got all of these massive problems affecting the planet, and is the argument about plastics merely taking us away from what's important? And what I hope I'll be able to show you over the next few slides is that, in fact, we cannot solve one without the other, because the climate change debate is the plastics debate and vice versa. And let's have a little look at what I mean by that. Well, we can go back to where we thought we started in terms of plastics and try and look for solutions to our design problems there. And the first plastics we made were around about 1907, when Leo Baekeland in New York discovered a thermosetting reaction between phenol and formaldehyde resin, and he started to produce this beautiful material called Bakelite. And you can see the mass production facility that he used to produce it here. And Bakelite was persistent, and it was durable, and it was available in all these beautiful colours. And in fact, when it was first made, it was seen as a very green and eco-friendly product, because it was sparing the use of horn and shell and tusk that would otherwise be used for these products. So it was saving the lives of many different animals in producing this alternative material. And it was highly prized to the extent that Bakelite items are now collector's items, which you can still find and have a very high value to them over 100 years later. So we'll move forward from that time to the 1990s, and what we discover is that things have changed hugely in those passing decades. And the discovery, particularly in the 1950s, of condensation reactions that produce polypropylene and polyethylene from petrochemical waste have led to a vast industry that produces hundreds of millions of tons of plastic a year. We haven't changed the design, so the plastic that we produce is as persistent and as resilient as the Bakelite that we produced in 1907. But somewhere along the way in those decades, we decided that it was okay to produce these materials and to throw them away. Now, if you think that currently over $16 billion has been invested in new petrochemical plants to convert petrochemicals into plastics in the last few years alone in the USA, you can see that this is a growing problem that is not going to go away. And current estimates are that we produce around 400 million tons of plastic. The estimate is that by 2050 we'll be producing 1,600 tons if we do things in the same way as we're doing at the moment. And of course, the issue is not just the plastic waste that's reaching the ocean in all parts of the ocean as shown by Kara's models, but it's also the carbon emissions that we're generating at the same time. So these are some estimates for the amount of global carbon emissions that are produced in relation to the plastics economy. And that includes plastics right through from their synthesis and use through to their disposal. And we can see that at the current day, around 3.8% of global carbon emissions are produced by the plastics industry. And to put that into context, that's over the amount that can be attributed to the aviation and shipping industries combined. So it's already a massive contributor to carbon emissions. If we continue to do things unchanged, then by 2050, over 17% of global carbon emissions will be produced by the plastics industry. So, as I said, the plastics industry and climate change are one and the same problem. It's not just carbon emissions, but we can start to see the source of the problem when we consider what we design plastics for. Because somewhere along the way, we kept their beauty and we kept their resilience, but we never asked the scientists in the 1950s who were learning how to polymerize and produce polypropylene and polyethylene to design in depolymerization reactions at the same time. And if we had, we perhaps wouldn't be facing this kind of crisis at the moment. And let's be clear, plastic is just one of the waste items we produce. As a society, as a global society, it's estimated that we produce 11 billion tons of waste material every year through our take, make, dispose, linear economic models. But luckily there is help at hand, and there is a solution if only we look for it. And I'll turn to the novel, or well, you could say novel, concept of the circular economy. And of course, this is not novel by any means, because the circular economy is what we've been doing for thousands of years until the last 50 years when we decided not to do it anymore. And the concepts of the circular economy are quite simple. There are three things that we should be doing. We should be designing out waste and pollution, so we don't accept them in our economic models in the first place. We should be keeping materials and products in use for longer, using them again and again. And we should be seeking to regenerate natural systems. So we're not just seeking to not just do less bad, but we're seeking to redesign the system and find value within it. Because let's face it, if we can't find value in what we're doing, if it costs too much money, then people are simply not going to do it. And in terms of plastics, we discovered that reduce, reuse, recycle, repair and replace are all the models that we seek to introduce to the system. And the good news is that if we turn to the circular economy, we can decarbonise. If you look at all of the modelled estimates, and these are some estimates from Zen and Sue at the University of Santa Barbara, then we can, if not reduce the carbon to zero, at least remove any increase that we might see as we increase our plastic production into the future. What these authors have done here is to estimate the carbon emissions from plastics if we use the current system, don't change anything, on the left. And on the right, they've estimated what would happen if we turned to a circular system. We used renewable energy, bio-based feedstocks, and we introduced recycling and reuse. So there is a solution, and it's there ready for us if we choose to take it. And of course, the question is, how on earth do we do that? And that's what I want to spend the rest of the talk talking about. And I want to introduce you to a large project that we've been working on for the last few years. And this is called the Exemplar Project. It's a multi-million-pound, multi-partner project based in the southwest of England and funded by the UK government. And you can have a look at the website and you can log in and you can get involved. And what is Exemplar seeking to do? Well, what we're doing is we're taking all the concepts and the ideas that Cara talked about on a global scale, and we're trying to recognise that if you want to actually find solutions, you have to test them out somewhere. So what we wanted to do here was to test them out regionally. And by doing that, we can more easily determine what's working and what isn't working, and what's ethically acceptable for people and what's economically viable. So our project, and the southwest of England is shown here, it's a region that has around about 1.9 million people living in it. So it's quite rural and it's not a particularly industrialised area. And within our project consortium, we have economists, we have sociologists and behavioural psychologists looking at what people will accept, including not just consumers, but the industrialists who make things. We've got life cycle assessment modelers, polymer engineers, ecotoxicologists, healthcare professionals, and we've got about 300 industrial and innovative companies, just some of whom are shown here. So we've got all sorts of bottom-up companies and initiatives based in the southwest who've joined in with our project. And I want to show you just one example of some of the things that we're doing. And this relates to, we've got interventions that are seeking to address the issues of fishing waste, of agricultural waste and household waste. And I'll talk you through one of the examples that we've been doing, looking at household waste in the southwest. So of course, if you want to understand the stocks and flows of plastics and change that system, then you have to know what those stocks and flows are. And using similar kinds of methods to those that Cara has been talking about, our life cycle analysts have been seeking to determine where all the stocks of plastics in the southwest of England are. And these results are in tonnes. And as we saw in Cara's results, the vast majority of the bulk of the plastic is in solid objects. It's in building products, it's in insulation panels, PVC windows, it's in household electrical items, it's in fridges and freezers, and there's a great deal of plastic in vehicles as well. Textiles account for some 80,000 tonnes in the southwest, and then there's some miscellaneous items. So the vast majority is in our buildings. But if we then turn to where the plastic is flowing, clearly a lot of the building materials, they're holding that stock, but they're not flowing through the system. And if we look at where the majority of the annual flow of plastic waste comes from, then it comes from household domestic waste. That dwarfs the amount that's coming from fishing gear and agriculture in the region, despite the fact that it's a high, fishing and agriculture are some of the main economies in the area. So household domestic waste, and if we probe into that further, we find that plastic milk bottles, plastic drinks bottles, and the plastic wrapping for fruit and vegetables and meats and dairy products are the vast majority of that household domestic waste. And then if we look at its fate and we look at where it's going, we see a very similar kind of picture to what Cara was finding in the United States. Only 4% of plastic is recycled in our region, which is a woefully low amount. The vast majority goes to landfill, and a high proportion goes to incineration in the southwest as well. So we've delineated a problem that centres around plastic bottles. And what we then want to do is to work out what to do about that and what might work in the region and what might not work. So we've got our problem, we're looking at its impact, we're looking for solutions, and we're looking for economic opportunities. And what I'll do is spend the rest of the talk talking about our impact assessment, because I'm an ecotoxicologist, I look at impact, and I've been working with the life cycle modelers and the human health team to determine what those impacts are. Excuse me. So let's look at our first example, and that's the life cycle modelling. And these are results which have been produced by my colleague Zhao Yan at the Environmental Sustainability Institute, who is part of the project. And what he's been doing is doing some life cycle assessments to determine what the effect would be if you took your typical PET plastic bottle in our region and you replaced it with glass. What would happen in terms of the environmental impact, including the carbon emissions that were produced? And what Jan did was he took 11 environmental indicators and pushed them together to produce what he called a global warming potential for the different materials. What he found was that if you were to replace the PET bottles with glass in the region, then you would double the global warming potential of those bottles. And that's because we don't produce any plastic and we don't produce much glass in the region, we import most of it. So a great deal of the global warming potential comes from transport costs. But a lot of the increase in global warming potential is because glass is heavier than plastic. So by doing some simple innovative modelling, they were able to show that if you simply made all of those glass bottles a bit thinner and a bit lighter, then you could return the carbon emissions down to what they would be for plastic, but you could remove the plastic. So interesting way to look at where your solution might have unintended consequences unless you take some remedial action. And this has just recently been published in Science of the Total Environment. Okay, so that's quite interesting. Let's turn to the human health impacts, because of course we've concentrated so far in this talk on carbon emissions, but as we all know, one of the main issues in terms of plastics is the chemicals that they contain. Plastic polymers are not just plastic polymers, but they're complex mixtures of polymers with many, many different additives, including intentionally added additives and unintentionally added substances that they pick up along the way. There are many different databases and many different authors have started to look at categorizing all of those. What I'm showing you here is a database that's been put together by the the Food Packaging Forum, which is an NGO initiative that has sought to identify the chemical additives that are most associated with plastic packaging, and also in particular those that might be of issue in a circular economy context. And that's because during the circular economy, not only do you have the additives that were in the initial plastic, but you've also got all of the additives that they pick up along the way, all of the unintended substances that are produced as plastics go through sort of cycles of thermosetting and recycling and resetting, and also the things that they pick up from perhaps the food that they've been carrying, so the odorants and the oils and the other contaminants. And as we can see, Grow et al. Found 906 different potential chemicals that were involved in this process, and they've listed in this database 148 of the most hazardous. Now, what we wanted to do was to do some evidence synthesis, because as anybody who's in clinical medicine knows, if you want to make a decision based on health impact, then you want to know what the strength of the evidence is. And we wanted to take a broader view and determine what the strength of the evidence was, that some of the main chemicals involved in circular economy context of plastic would be in terms of human health. What kind of implications would it have to increase recycling? And just to tell you how this project is progressing, we have been asking questions including the likelihood of impact by recycling processes, the frequency of use in primary plastic products, and the human health hazard score. And interestingly, Jacqueline Earls and Ruth Garside, who've been doing most of this work, found that 6 out of the 6 top scoring substances were phthalates. And they are well on the way with their evidence synthesis of all the human health impacts of phthalates. And we're hoping that these results will be published early next year. Okay, so let's turn to the ecotoxicology part of the project. What have we been doing there and what have we been finding? Well, we've been looking at what some of the alternatives, or some of the bioplastic alternatives to those petrochemical plastic bottles would be in terms of their ecotoxicology impact. And we've been working with here in terms of bioplastics with a company called Materium. And they specialize in making plastics from waste products. And in this case, the image you can see on the right are plastic bottles that are made out of algal seaweed waste. Now, bioplastics have a number of positives. They're sustainably derived, in this case seaweed. They're biodegradable. One of the positives is that it decouples plastics from the oil industry, so you're less influenced by that ever-increasing industry of petrochemical need. One of the negatives is that quite frequently these materials still show inferior performance. You can see here, this isn't quite your clear Coke bottle that you might want to be selling to people just yet. At the moment, most of the bioplastics still cost a bit more than your traditional plastics, and more importantly, they have unknown ecological effects. Secondly, we've been looking at what would happen if you replaced some of those plastic containers with recycled plastics. And here we've been working with a company called A Short Walk, who have recently been renamed Circular & Co. And we've been looking at their R cup, which is a reusable cup that's made from used cups. The company reckons they've produced about 5.4 million cups at the moment. So those cups are being reused. And they've done some estimates that suggest that this has saved 17 billion single-use cup events from taking place since they started producing the cups. So that's a positive. On the negative, as you recycle many petrochemical plastics, you start to see reduced mechanical performance, you start to see molecular degradation, but in addition, you start to see contamination. So we were interested to compare these two different kinds of plastics and see how they compared with the traditional plastics. And excellent postdoc Paul Boisseau has been doing ecotoxicity test panels to determine what might be happening with some of these materials. He's been doing acute and chronic tests with freshwater and marine species, in this case Daphnia magna, the water flea, and Artemia, the brine shrimp. Chronic tests include a wide range of different sublethal responses, and he's also been doing multi-generational tests to determine what might be happening over subsequent generations exposed to these materials. And what is the test panel that we've been using, and how have we been using them? Well, all of the materials I've just talked about. We've been trying to use the virgin materials in pellet and or flake form. We've been trying to look at the materials that are made out of them. We've been comparing the recycled plastics and the biopolymer alternatives. And what we've been doing is we've been freeze grinding in a cryo grinder the materials, generating microplastics, dry sieving them to different size ranges, and making aqueous leachates. So we've been doing 48-hour aquatic leachates into water. We've also been determining what happens with the microplastics when you put them into mixtures with other common persistent pollutants that we commonly find in the environment. How do they compare in terms of how they bind, and do they have any synergistic or antagonistic effects? And this is all very new, and this has all been delayed hugely due to the COVID epidemic, but we have been getting back into the lab over the summer and starting to produce some results. And these are some of the results for the biopolymers. We find that in general they show low toxicity in these in vivo studies, and the LC10 to LC50s are in the gram per litre range. And I thought I'd try to compare that against some of my colleague Martin Wagner and his team's recent published results. They've been doing in vitro panels of testing for comparing different biopolymers and different starch and cellulose-based polymers. And I've made an estimate. Their results are presented in terms of an EC20, in terms of using mgs per well of plastic. So I've sort of done a bit of a rough estimate of what that means in terms of grams per litre, and come up with a figure of 4 grams per litre. Martin might want to take me up on that afterwards, but that's my best estimate. And what they found was that cellulose and starch biopolymers were actually more toxic than some of the other polymers that they were studying. It looks like we're getting roughly similar. I think we're getting higher levels of toxicity in our in vivo assays than perhaps the in vitro screen. But of course, we're looking at different materials. What we've also seen in some of these early results is that we see growth promoting effects at low concentrations. This is perhaps unsurprising as we're releasing carbon equivalents into the water column. And we've been doing quite a bit of work on what those growth promoting effects might be and how they affect the subsequent growth, reproduction and fecundity of the animals. And another interesting point is that what we find in producing the hydrosols from some of the biopolymers, which dissolve into the water column to make these sort of gel-like substances, is that they alter the water chemistry. And these results are illustrating to you that we see changes, particularly in the pH of our exposure waters, as we work with these materials. The interesting point here is that currently about 99% of plastic production, that 400 million tonnes of plastic production, is petrochemicals, and they don't dissolve at all and they produce microplastics. Only 1% of current production is attributable to biopolymers. 2030 EU targets so that we're going to change that so that 65% of what we produce should be biopolymers. And if we continue to extrapolate beyond the 400 million to 1600 million tonnes of plastic production, we've got to think carefully about what's going to happen to some of those biopolymers if we think that we can continue to use them and people are encouraged to throw them away in the same magnitude as we're throwing away our current plastics. Okay, so that was a bit of a whistle-stop tour around what we're trying to do in terms of solutions. The conclusions I'd like to say is that creating circular economy inspired solutions is a multi-layered, multi-scale challenge. Clearly, you've got to have many different people working in different, looking at different consequences and unintended consequences. It's best if you look at the economic, the environmental, the health, the cost, and the policy implications of the things that you're trying to design in. There is no single answer. There's going to be multiple solutions to these problems. And I thought I'd show you this vintage Bakelite telephone, 100 years old and still going strong. And I'll finish there. thank everybody who's been involved in the exemplar product and everybody else in the ecotoxicology group at Exeter, and all of my collaborators around the world, and happy to take any questions.